So in this video I'm going to continue with chapter 18 and we're going to have a look at graphs, the concentration time graphs first and then rate concentration graphs second. So your concentration time graphs, I'll draw one out. I've got concentration on the y-axis and I have got time on the x-axis. And the reason these graphs are useful is you can use these graphs to calculate the rate of reaction at any time. You can also use these graphs to work out the order with respect to a particular reactant. So once you've got your data, you've got your concentration and how it's changing over time, and if you don't know how to calculate that, go back and watch the previous video on colorimetry. It's one of the common methods used. But once you've got this data, you can plot a graph. So there's a few different shapes, and you need to know what the shape tells you about the order and also how you would calculate the rate. So I'm going to draw one that looks like this, and it's a straight line. And the question might ask you what is, so this would be, so let's say we were looking at a reaction that involved iodine. This graph would just be showing how the concentration of iodine changes over the course of the reaction. So you'd be looking specifically at one reactant. In this case, we're going to look at iodine. And they might ask you what is the order with respect to iodine. When you get a graph, a concentration time graph that has this shape, it is going to be a zero order reaction. And rather than just learning that off by heart, and you might get confused in the exam, it's best to understand exactly why that is the case. So what we can see here is that the concentration is decreasing over time. Okay, that's expected. If iodine is one of the reactants, it is going to be used up in the reaction. You expect its concentration to decrease over time. Okay, regardless of the order, the concentration is going to decrease over time as the reactant gets used up. Okay, but what we can see here is if I wanted to actually work out the rate of this reaction, what I would do is I would get the gradient of the line. And because the line is a straight line, the gradient is exactly the same at every time point. And because the gradient is the same at every time point, the rate is the same at every time point. So in other words, the rate is unchanged, even though the concentration of iodine is decreasing. So I'm going to write it here. This graph shows, that the concentration of I2 decreases. The graph also shows that the rate remains constant. How is it showing that the rate remains constant? Because the graph is a straight line. And because it's a straight line, the gradient is exactly the same at every point. If the rate stays the same, even though you're decreasing the concentration of iodine, then I can say the concentration of iodine has no effect on the rate, therefore iodine must be a zero order reactant. So they'll all look like this for a zero order reactant, but it is best to be able to kind of think through the process as opposed to just learning it off by heart. I can also work out my rate constant K. And again, if you don't know what I'm talking about when I say rate constant K, please go back and watch one of my previous videos. All right, we've just said that I2 is zero order, so I can write a rate equation then. It would be K times I2 to the power of 0. All right, anything to the power of 0 is 1. So I can get rid of that, and I'm just left with rate equals K. So when I get the gradient tells me the rate, but in this case, the gradient is also going to tell me K. So rate equals the gradient, and it equals K. They are all equal. So if I want to find out K, I get the gradient of the line. If I want to find out the rate, I get the gradient of the line. And no matter which one you're asked for, you're just going to be getting the gradient of that line. Right, we're going to look at another example. Again, I'm just kind of making this up. And this time I'm going to look at the concentration of, let's say I have an acid involved in my reaction, and I'm looking at how the concentration of my acid changes over time. Again, because my acid is one of my reactants, it is going to be used up over the course of the reaction, and I know the concentration is going to decrease. But in this case, instead of getting a dead straight line, what I see is that I end up with a curve, something that looks like this. Okay, so again, I can see that my concentration is decreasing over the time, but this time my rate is not remaining constant. So I'm just going to write below what I can see from the graph. The graph shows that I'm getting a decrease in the concentration of my acid, okay, but this time rate is not constant. All right, and hopefully it's quite obvious how I know that, but I'll show you if not, okay? If I wanted to get the rate of at this graph, okay, what I would need to do is I would need to draw a tangent at different time points. So let's just say I wanted to know what the rate of the reaction was at this point here. Okay, so just say this is 10 seconds. I would have to go to my graph, I would have to draw a tangent, and I would have to get the gradient of that line, and that would tell me the rate at that particular time point. Let's just say I was interested in this time point down here. I'd go to that point on the graph, I would draw myself a tangent at that point. I would draw myself a tangent at the point, and I would get the gradient of that line to work out what the rate was at that point. And what we can clearly see here, that the two tangents that I've drawn, they are going to have very different gradients. This line here is obviously very, very steep. This line here, a lot less so. So I'm going to get different gradients, therefore I'm going to have different rates. So rate is not constant. You've got a curve. Because you've got a curve, the gradient is changing. So what this is showing me, okay, the fact that the graph starts off really steep, that's telling me that the rate is quicker, and then my rate slows down. Okay, so the steeper that line, the quicker the rate. As it slows down, the curve levels off. So I know my concentration of H plus is decreasing, and as my concentration of H plus decreases, as I've got less H plus in my flask, my rate is slowing down. Okay, so the concentration of H plus is having an effect on the rate. It's definitely not zero order, but it could be first order, or it could be second, okay, because that would be true for both of them. If you decrease a first order or second order reactant, if you decrease its concentration, it is going to slow the rate down. And if you had a first order and a second order graph side by side, you might be able to spot the difference. With a second order, it should be even steeper at the start before it levels off. And with the first order, it should be slightly less steep. And when I've got them side by side, we can see that this one here on the right hand side is steeper. But when you've just got one by itself, how are you supposed to know if it's first or second when they both have generally the same shape? And that's where half-life comes into it. Okay, so I've got, I have an example here. Okay, half-life. Oop, change me. So I have my concentration time graph here. As you can see, concentration decreasing over time, but because it's a curve, I know it's not zero order. It could be first, it could be second. To show that it's first, I can use half-life. I go here to my concentration. I see my starting concentration is 0.1. I then need to get half of the concentration. So half of 0.1 is 0.05. And I need to look at the time it took for that concentration to half. So I'm starting here at 0, and it took 100 seconds for the concentration to half. So my first T at half is 100 seconds. Now I'm starting here at 0.05. What's half of 0.05? 0.025. So I need to look and see how long did it take it to go from 0.05 to 0.25. And again, I can see that that took 100 seconds. 0.025, half of that is 12.5. So I go to 12.5, I go across and I go down. This is the time point when it was at 25. This is the time point that it's on 12.5. Again, it took 100 seconds for it to half. And what we can say is that if you have constant half-life, so if the half-life is the same each time, then it is a first order reaction. In practice, if you're doing this, it's not going to work out quite so neatly as what it has done in the book. If you worked out that your first half-life was 60 seconds and you worked out your next one was 62 and then your third one was 61, that would be fine. You would still say that they were constant, okay? If you worked out your first one was 60 and your next one was 200, then obviously they're not. And if you do have a constant half-life, then you can say that the reactant is first order. So in this case, the reactant that we're looking at is N2O5. I can say that the N2O5 is a first order reactant. If you did the half-life, you had the shape of a graph and you did the half-life and it was not constant, you can't conclude that it's second order. You can just say that it's definitely not first. It doesn't mean that it's second, it just means that it is definitely not first order. So when I get a graph that looks like this, okay, likely first order, but I can't say for sure. I have to use half-life before I can confirm that it is first order. With this graph up here, when I see this shape, I know it's zero order straight away, but this one down here, I need to confirm it's first order by showing it's got a constant half-life. Okay, so once you've established that you do indeed have a first order reactant, you've got a first order graph, there's a few different things that you can do. If you're asked to calculate the rate, as we've also said, you would need to draw tangents at different points. So they would ask you at a specific time point what the rate was, you draw a tangent, you get the gradient, and that will be the rate at that specific time point. Obviously the rate is changing, so there's not one rate for the whole reaction, it changes as the reaction progresses, it slows down. The other thing they can ask you for is determine K for a first order reaction. Now, with our zero order reaction, this was very straightforward. We used our rate equation, and we saw that when we simplified our equation, whatever you got for the rate was equal to K, all right? That's not going to work here. The rate is different at different points, and K can't change. So I can't just have rate equals K like I did for a zero order reaction. So you've got two ways that you can calculate K. One, I would say, is easier than the other. So what you can do is, again, you can use your rate equation, and you can write rate equals K times the concentration of our H plus. And this time, because it's first order, that's not going to disappear. And what I can do is I can rearrange that equation to solve for K, and I can write, over here, I can write K equals rate over the concentration of H plus. And what I would then need to do is I would need to pick a particular time point. Let's say I pick this time point, and I would need to draw a tangent, and I would need to calculate the gradient. And once I've done that, I know the rate at that particular time, and I can plug that number in there for rate. And then for the concentration of H plus, whatever the time point is that I've chosen, I'll go across the y-axis and I'll read the concentration of H plus off the y-axis, and I'll plug that in as well. So I could pick any time point on the graph, okay? I could pick this time point right here. I could draw myself a tangent, calculate the gradient of the tangent, and plug that number in for rate. And then for concentration, I would just move across, read the value from the y-axis, and plug that in for concentration. And in that way, I would be able to calculate K. Now, obviously that is a bit long because getting the rate involves getting the gradient, so drawing tangents. And luckily there is a quicker way. If you've established that it's definitely a first order reaction, and you know you've got a constant half-life, what you can use instead is K equals log 2 over T a half. So if they ask you earlier on in the question to show that it's first order, and you've already gone through and you've calculated the half-life, let's just say the half-life is 60 seconds, then you can just do log 2 over 60 to calculate K. I just want to show you log. Now I'm saying the word log, all right, but there's two buttons on your calculator. Actually, there's three buttons on your calculator that have log, and you're going to be using this one, LN, not that one, not LOG, you're using LN. And you type in LN, and you type in 2, and you press equals, and you get that value there. When you're doing it on your calculator, it's really important to make sure you can do it. So I want log 2. I would have to close that bracket if I wanted to just divide by 60 straight away. Okay? If I don't close that bracket, if I go log 2 divide by 60, I end up with an entirely different answer. So it's that one there, ln, to close the bracket, and then divide by whatever your half-life is. In this case, we're saying it's 60 seconds, and you're going to work out K. And that doesn't involve drawing tangents or calculating gradients, so it is an easier method. That's not given to you in your equation sheets. You need to learn that off by heart. So in a general summary, all right, if I've got a concentration time graph, I've got concentration versus time, all right, there are two orders that you need to be able to look for, all right, if you've got a 0 order reactant compared to if you've got a first order. And if it's a 0 order, the shape of the graph should look like this, and if it's a first order, the shape of the graph should look like this. If I want to calculate the rate, okay, I just need to get the gradient of the line. If I want to get the rate over here, I need to get the gradient of a tangent at a specific time point. So they'll tell you a time, you draw a tangent, and you'll get the rate at a specific time point because the rate keeps changing. Here the rate stays constant. If I want to calculate K, okay, I can use my rate equation, all right, because I know this is a 0 order reaction. So let's say it's A. Then I know that my rate equals K. So once I know my gradient equals rate, and my gradient also equals K. So I can write that the gradient of that one line is going to equal K. Okay, but over here, when I write my rate equation for a first order, that is not going to disappear, and when I rearrange for K, I get rate over concentration. I can do this by finding the rate at a specific time point by drawing a tangent and then reading the concentration at that same point. Or my other method is I can find K by doing log 2 over T1/2. And that is typically your easier method. Okay, if they've already asked you to confirm that it's first order by showing it's got a constant half-life and you've already got the half-life, then that is going to be your easier method. Again, a second order would have a similar shape. The way I know it's definitely first is because it's got what we call a constant half-life. There are loads of questions in your booklet on this. A lot of them involve drawing graphs. You need to practice drawing graphs, okay? You need to practice drawing your tangents and getting the gradient of the tangent to make sure that you can get your answer within the right range. There won't just be one right answer, you will have a range, but you need to make sure you're drawing your tangents correctly, that you're not making it too steep. You need to make sure you're doing it correctly, and the only way to do that is practice. So there's tons of questions in the book. I would advise doing all of them, including all the ones that involve drawing graphs, just so you get really, really good at drawing your graphs and drawing your tangents. Next video, I'm going to look at the rate concentration graphs, which have different shapes depending on whether they're 0 first or second order.